Okay, so welcome everyone to Valentine's Day lecture to the seminar today. So I'm delighted to present Kengo Kato, who originally was trained in economics, but has moved into statistics and is at Cornell and is now editor-in-chief of Bernoulli and among many other audits, and who will be talking to us on entropic optimal transport and Gromov-Wasserstein alignment.
Thank you very much for the invitation. I'm very happy to have talk at Washington. This is Valentine's Day, so I brought some chocolates to to the seminar room. So if you have time, then please pick up chocolates. Anyway, so today I will discuss my recent work on entropic optimal transport and Gromov-Wasserstein alignment. So this talk is based on joint work with my collaborators, David Goldfeld, who is a faculty in the EC department of Cornell, and our students, Gabriel Rio and Ritvik Sadhu. So Ritvik is currently doing postdoc at U Washington. He's there. So I will first briefly overview OT and entropic OT, and then move on to my own research. So these are pictures of Monge and Kantorovich and Schrödinger. So these are founders of OT and entropic OT. So OT theory goes back to Monge. So in modern language, Monge considers the following problem. So suppose you're given some marginal distributions, and you want to find a map that transports input measure mu to output measure mu in such a way that cost is minimized, aggregated cost is minimized. Okay, so so this formulation is quite intuitive in the sense that we are basically mapping random point into a random point, and mapped point random point should follow the given target given output marginal. Okay, so this is quite intuitive, but this is not actually most convenient way formulation of optimal transport. In fact, think about following case. Suppose we want to transport bread from bakeries to cafes. Okay, we have a set of bakeries and we have a set of cafes. We want to transport bread from bakeries to cafes. Okay, and then each bakery is producing certain portion of bread. Then each cafe is consuming certain portion of bread. Okay, so we have two discrete marginals on the bakeries and cafes. Okay, and then Monge problem is asking each bakery to transport bread to only one cafe. Okay, so that is building a mapping, right? But then it is evident that if there are more cafes than bakeries, there is no transport map at all. Okay, but because in this case you cannot exhaust all cafes. Okay, because there are more cafes than bakeries. Okay, so in general, the Monge problem is ill-posed because in some cases the domain is empty, so infeasible in general. Okay, and then Kantorovich formulation is basically kind of relaxation of the Monge problem. Instead of finding a map, we are trying to find a coupling that minimizes the expected cost. Okay, so keep in mind that once there is a transport map, okay, like this, then this pair is inducing a coupling. Okay, by coupling, I mean that the joint distribution with marginals mu and nu. So once you have a coupling, if it exists, then this pair is inducing a coupling. Okay, so the Kantorovich relaxation is basically dropping the requirement that each coupling is induced by a map. Okay? So this is the relaxation, right? And also, in the Rata formulation, there's always at least one coupling, right? So you can take the product of three marginals. That is the valid coupling. So this domain is non-empty. And also, as long as the cost function is lower semi-continuous, which is a very weak assumption, there is always at least one optimal solution to the Kantorovich problem, okay? Which is more convenient than the Monge problem. Okay? So OT theory has seen many applications in various fields. The one thing is that OT cost is quantifying how difficult you transport one measure to the other. So it is natural that OT cost induces a metric on the space of probability measures. Okay. For example, Wasserstein distance is a special case of the OT cost. You have to do some normalization to make sure that this is indeed a metric. Okay. And Wasserstein distance has similar applications in statistics. For example, in parametric estimation, you might have had a Wasserstein GAN, and also various testing problems. For recent development of statistical OT, I will recommend you look at the monographs by Pantos and Zemel, and Chewy, Niceweed, and Rigore. Okay, so in addition to OT cost, one more important concept in OT theory is the Grenier map. Okay? So I said that Monge problem is in general imposed in the sense that there might be no transport map transporting mu to mu, but under some conditions on the cost and margin, input marginal, Monge problem is indeed opposed. So one canonical situation is the case where the cost function is a squared norm, and input measure is absolutely continuous. In that case, there is a unique optimal solution to the Monge problem, which is given by the gradient of some convex function. And also there's a reverse implication of this theorem, saying that if you have a transport map given by the gradient of some convex function, then that map must be a optimal solution to the Monge problem. Okay, so these conditions are characterizing a map to be optimal for the Monge problem. Okay, so Grenier map has many applications. Even in pure mathematics, it has been used to provide short proofs of functional inequalities such as log concave inequality and HWI inequality. And statistically, it has nice interpretation as being a multivariate quantized function. Okay, so in fact, when d is equal to 1, a dimension is 1, then the Grenier map is nothing but the composition of the quantized function of the output and the CDF of the input. Okay, so if you normalize input distribution to be uniform, then the Grenier map coincides with the quantized function. Okay? And also, Grenier map shares important properties of the quantized function. One is that it is monotone because it is a gradient of convex function, and also it is transfer map so that you can recover the target distribution from this transport map. Okay, so we can think of Grenier map as a quantized function in higher dimension. So this is actually a nice interpretation of the Grenier map in statistical setting. Okay, so that's fine, but then in practice we have to compute and estimate the OT cost and Grenier map. But then estimation of the OT cost and Grenier map suffers from because of dimensionality. Okay, for example, natural way to estimate Wasserstein distance is to plug in empirical distributions into marginal distributions. Here, I'm assuming that we have IID data from each marginal, and then plug in empirical distributions into mu and nu. Okay, so these are nu hat n and nu hat n. Okay, then what happens that you end up with rate into the power of -1 over d, where d is the dimension of the support. Okay, and also this rate is known to be sharp, and actually you can get faster rate, but then you have to assume very strong assumptions on the two marginals, which you may not like to impose. Okay, and also similar rates hold for the Grenier map estimation. Okay? So Grenier map case is a bit subtle, but you can think of the following setting. So Grenier map can be seen as a multivariate quantized function. So it is natural to assume that input measure is known. Okay, assume that input measure is known, then the only unknown is output. Okay, and then we have a sample from the output distribution nu. Okay, and then because nu is absolutely continuous, we can compute the Grenier map transporting nu to the empirical distribution of nu. So that will give you a plugin estimator of the Grenier map. Then if you use the L2 loss function, what you get is this rate. So you end up with into the power 1 over d rate for the Grenier map estimation. Okay, and also the computation of OT cost is also non-trivial. So OT problem is a linear program, so you can actually exactly compute the OT cost. But then computational cost of OT cost is proportional to n cubed when two marginals are supported at endpoints, which may not be quite appealing in modern applications. Okay. Any questions up to this one? No? All right, so so entropic OT emerged as a way to mitigate those two bottlenecks. So the idea goes back to Schrodinger. So he has in mind something different. He has in mind some dynamical problem. So what he has in mind is basically to kind of find the best. Okay, so you have some Brownian motion or Wheeler measure, and he wanted to kind of find the entropic projection of Brownian motion onto the space of path measures with given initial and terminal distribution. Okay? And it's not difficult to see that that problem, that dynamical problem, is equivalent to solving this entropic transfer problem. Okay? So that's why, so this problem is often called Schrodinger problem. Okay? So entropic OT is simply putting the entropic penalty to the Kantorovich objective. Okay? Okay. And the reason why entropic OT has become quite popular is because you can efficiently compute entropic OT by using so-called synchrone algorithm, whose complexity is n squared instead of n cubed. Okay? And also, as you can imagine, when epsilon is 0, this is nothing but the Kantorovich modulation. So you can imagine that when epsilon is going to 0, then OT cost would approximate OT cost itself, unregularized OT cost. Okay, so this is actually the case. And I should mention that there's a tons of papers on this topic, how this entropic OT approximates OT. So I only point to one paper, but you can actually find many papers on this topic. Okay, and I think Schmidt has also has one nice paper on this topic, and also many other papers on this topic. Okay. Okay, so so this KO divergence penalty is convex in the first coordinate, actually strictly convex in the first coordinate, and then first term is linear in pi. So the entire objective function is strictly convex in pi. Okay, so because of that, there's always unique optimal solution to the entropic OT problem. Okay? And that unique optimal solution is given by this formula, where you see two functions. Okay, so there are two functions which I call entropic potentials that characterize the entropic unique optimal coupling for the EOT problem. Okay. So as far as entropic transport is concerned, entropic potentials govern everything, govern the entropic coupling. So if you want to analyze entropic transport, it's enough to look at entropic potentials. Okay? And for example, you can express the entropic cost using the entropic potentials like this. Okay? So this is simply just plugging in this formula into the above objective. Okay? After doing some mathematics, after doing some algebra, you get this expression, which is kind of similar to dual form of the unregularized OT cost. Okay? Any questions? Okay. All right, so there's also an entropic analog of the Brenier map, which is called entropic map. So the idea is the following. So if there is the Brenier map, then the corresponding OT coupling is concentric on the graph of the Brenier map. Okay, so under the OT coupling, if you condition on the first coordinate, then the second coordinate is exactly equal to the OT map, the Brenier map at that point. Okay, so this is not the case for the entropic coupling. Okay, but you can take the conditional expectation. You fix the first coordinate and take the conditional expectation with respect to the second coordinate under the entropic coupling. Okay, so this will give you something like surrogate of the Brenier map. Okay? And also you can express this entropic map using the gradient of the first potential. Right? And also you can imagine and also when epsilon is going to 0, the entropic map approximates the Brenier map. Okay? This is a canonical rate, but you can also see different rates depending on the assumptions. Okay, so if you make some strong assumptions, you can make faster. You can make this rate faster. Okay. Any questions? Okay. All right, so let's move on. All right, so okay, so for estimation, if you really think that we are interested in like entropic OT itself, meaning that if you fix epsilon, then you get parametric complexity, complexity for both cost and map. Okay, so this is a huge contrast with the OT case. Okay, so there's always like some discussion about how to make sense of this fixed epsilon analysis. But for example, like Rigore and Strom, they kind of discuss one way of justifying this analysis by interpreting this EOT from the stochastic variational analysis. But anyway, the point is that initially an entropic OT emerged as something approximating OT itself, OT. But then people realized that EOT has very nice properties, like computational and statistical properties. So so then people started by thinking of entropic OT itself. Okay? So we are interested in entropic OT itself, not just approximating OT. Okay? So here I'm looking at entropic OT itself and try to understand the properties of the entropic OT, how we can do inference for the entropic OT. Right? Okay, so given these like sample complexity results, the next natural question is to find asymptotic distributions of the entropic cost and entropic map and other potential quantities of interest for the entropic OT. Okay? For the discrete case, where we have two discrete marginals, then I think these two papers, have already done some satisfactory, limit distribution theory for the entropic OT. So in discrete case, you can always parameterize each marginal by finite dimensional vector. So everything is parametric. Okay, in that case, you can do like some, you can apply basically standard estimation machinery to get asymptotic distributions for cost and map and other things as well. Okay? But of course, this argument does not carry over to like more general case. So we wanted to kind of develop a unified limit theory for the entropic cost, entropic ultimate transport with general marginals that can lead to asymptotic distributions of several objects of interest in OT under the same umbrella. Okay, so that motivates the this paper, which was accepted last year by EJS. Right. So the question we are addressing in that paper is the following. Okay. So I said that when you want to analyze the EOT, it's enough to look at the entropic potentials, right? So the question we are addressing in that paper is, so can we differentiate the mapping from the pair of marginals into the pair of entropic potentials? Okay. Okay. So the idea is that once we can, we can kind of make sense of this operation, this differentiation, then we can possibly combine functional data method to get limit distributions for the potentials. And from there, we can also derive other asymptotic distributions for the cost and also other things, okay? Cost and map. Okay? So here I'm making assumption that C's cost function is smooth and two marginals are compactly supported. Okay? So X is the common set containing the supports of two marginals. Okay? So under these assumptions, entropic potentials are smooth on X. Okay, so these are simply smooth. Smoothness is in the sense of the argument, right? Not this mapping, right? Okay. Okay, so to make sense of, yeah, go ahead. You don't have to take epsilon to be 1. In practice, I don't know how to choose epsilon, to be honest, but you can choose epsilon to be 1 if you want to make the story easy. Okay. All right. So, okay. So because now entropic potentials are smooth, so we can think of each element of potentials to be an element of some smooth function class. Okay? So to make sense of this differentiation, you have to specify the space for the measures and space for the potentials, right? Because in this case, entropic potentials is smooth, you can choose some smooth function class for the potentials, right? But still, this differentiation doesn't make sense as is, because the space of probability measures is not a vector space. The difference of two probability measures is not a probability measure. It's not probability measure. So the space of probability measures is not a vector space. Okay. So to make sense of this operation, you have to find some space onto which we can embed each marginal. Some suitable space, suitable known space on which we can embed each marginal. Okay. So actually it turns out that the following setting works quite well for our purpose. Okay. So what we have done is the following. So we pick any positive constant, positive integer, which is accounting for the smoothness of the potentials. We then embed each marginal into the dual space of order space with smoothness S. Okay? And then think of this mapping as a mapping from the dual space of CS into CS. CS is the order space with index S. Okay? So as this mapping, the entropic potentials are Hadamard differentiable in a suitable sense. So I'm not going to, I'm not going to explain what Hadamard differentiability is. You can basically consult John's book with Vandervaart. But anyway, the point is that Hadamard differentiability is strong enough to extend the functional delta method. Okay? It is somewhere between pressure differentiability and Kato differentiability. Okay, so Hadamard differentiability is weaker than pressure differentiability, but stronger than Kato differentiability. Okay? Strong enough to extend the functional delta method. Okay? And keep in mind that this S is arbitrary, so you can choose S large enough. So when you choose S large enough, then the empirical process based on IID data satisfy a COT in the dual space, in the dual order space. Okay. So this is kind of classical result in empirical process theory. So now you can combine the functional delta method to get COTs for the Planck estimators of the potentials and also the map. Okay. Simply because in this case, map is essentially given by the gradient of the potential. Okay? And potential is differentiable as a mapping into C space. Okay, so if you reduce index by 1, then this map is also Hadamard differentiable as a function of two marginals, as a mapping into the space, this space. Okay. So I should also mention that there is some concurrent work by Gunsius and Xu and Gonzalez and San et al. I'm happy to talk about relation between with these two papers offline. Okay. Anyway, so this is the first result. Okay. So let me talk about some proof technique idea. So entropy coupling must be coupling so that it has marginals near mu. Okay. So this implies that entropic potentials satisfy the Schrodinger system. Okay. So the first equation simply says that the entropy coupling has marginal mu on the first coordinate. And the second equation says that entropy coupling has marginal mu on the second coordinate. Okay, so if you look back at the definition of the entropy coupling, then you see that I'm simply integrating out the second coordinate, first coordinate in the Schrodinger system. Okay? Right? Okay. So this can be seen as a functional equation for two potentials, and actually, up to some normalization, entropic potentials are unique solutions to this functional equation. So given this, it is natural to apply some kind of implicit function theorem to get the derivatives of the entropic potentials as functions of two marginals. Okay. So this is the basic idea. But of course, there's a lot of functional analytic argument in the proof. So the proof is actually not quite easy. But anyway, this is something we have done for the proof. Any questions about proof? No? Okay. So actually in the paper, we also get the second differentiability. So which was somehow needed because we wanted to also get limiting distribution of the sinkhorn divergence, which is kind of symmetrized version of the entropic cost. Okay, and sinkhorn divergence, that's a derivative 0 when you have the same margins. Okay, so you have to look at the high order term when you want to get the limiting distribution for the sinkhorn divergence when you have two identical population margins. Okay. To that end, we needed to get the higher order derivative of the entropic potentials. So so somehow we kind of extended some version of implicit function theorem to get the second derivative of the entropic potentials. Okay. Any questions? Okay. Yeah, they must be supported, completely supported. Yeah. So there's actually one technical complication. So possibly we could kind of work on unbounded support, but then you have to kind of find nice, function space. Maybe possibly you have to devise some kind of weighted order space. But in that case, I think your space might be a bit complicated. So I wanted to avoid that complications. Okay. Okay, so let's move on to the second part about Gromov-Wasserstein alignment. So, okay, so this part is based on two papers. First paper was accepted to JML recently, and the second paper was posted recently. So it was still waiting for the first decision. Anyway, so the topic is somehow, you might think that topic is somehow distant from the first part, but actually, technically speaking, there's a lot of similarity between analysis. Okay, so that's why I wanted to talk about these two things in one talk. Okay, so what is Gromov-Wasserstein distance? Gromov-Wasserstein distance is a metric. It's basically comparing two metric measure spaces. Okay, so we are not just comparing marginals, we are comparing metric structures, right, of the space. Okay. So definition is here. So basically, kind of in this definition, metric structure come into play when you compare two marginals. Right? Okay, for example, and then so this Gromov-Wasserstein defines a metric on space of all metric measure spaces up to some measure preserving as matrices. Okay? And also applications include large language alignment, shape and matching, shape and graph matching, and so on. So in these applications, you have some metric structures, and you want to kind of you want to take into account metric structures when you compare two marks. Okay. Okay. Right. So so that's fine. But then what happens is that so this GW cost objective is nonlinear in pi because now we have to generate two independent samples from the same coupling, so that this is actually bilinear programming problem. Okay, so this objective is non-convex, nonlinear, and non-convex. So the computing GW distance is quite difficult. In fact, when you have two discrete marginals supported on endpoints, then this GW problem is equivalent to quadratic assignment problem, which is known to be NP complete. Right? So challenge here is that computation is quite difficult. So OT case, OT cost is just near program. So anyway, so the computational cost is big, but anyway, you can solve it, right? But in this case, GW is non-convex and bilinear programming problem, and also it is known to be NP complete. Okay, so the computation is quite difficult for the GW case. So then it's not so because of this motivated Perrier-Doll to propose like putting entropic penalty, okay, to mitigate this computational difficulty. Okay, So definition is kind of similar to entropic OT. You are simply, adding entropy penalty to the GW objective. Okay. So you are having the same entropy penalty as in entropic OT. Okay. So, and then the goal in the paper I show, the first paper I showed, is to give some formal computational guarantees for EGW, which was missing. Okay. Okay. So actually in this talk, I'm focusing on the setting where the two metric measure spaces are Euclidean spaces. Okay. But dimensions can be different. So dx and dy can be different. So we can deal with unequal dimensions. Okay. The key, and also I focus on the case where P and Q, so these are indices for GW problem, 2 and 2. Okay. So in that setting, so there is a key variational representation of the GW distance, which is given by Zhenxi Zhang, who's a student of Zilberfeld, which basically connects the GW problem, entropic GW problem, with the standard EOT problem. Okay? So here, the first term depends only on the moments of the marginals. So you can easily compute the first term. Okay? So what is more difficult is the second term. The second term has this EOT cost, but the point is that this cost function, okay, for the EOT problem depends on the matrix, auxiliary matrix A, and we need to minimize this EOT cost that depends on A, subject to this penalization, okay, over the entire matrix space. Okay. So, so this is nice, but still, we need to minimize the second term, which is highly non-trivial because EOT, so this EOT cost depends on matrix A in rather complicated way, right? Because this matrix A is appearing in the cost, but then EOT cost is basically kind of obtained by minimizing the objective over the all couplings, right? For mu and nu. So dependence on EOT cost on the matrix A is quite complicated. So so it's not clear at all how we can minimize the second function. Okay. So the basic question we address in the paper is to understand whether phi function is smooth and when phi function is convex. Okay. Okay. So if you look back at the definition of entropic GW, then when epsilon is large enough, then in that case, when epsilon is large enough, then the penalty term dominates the first term, right? The first term is non-linear, non-convex, but second term is strictly convex in phi. Okay, so if epsilon is large enough, then you can imagine that the whole objective is convex. Okay, so you can imagine that when epsilon is large enough, then phi function is convex. Okay? But we need to understand the quantitative threshold under which the entropic this phi function is actually convex. Okay, so these are questions we addressed in the paper I showed. Okay, so let me show the results. Okay, so phi function is convex if epsilon is larger than this, the 16 times square root of the fourth moment, product of fourth moments, and phi function is L smooth with L at most this number. Okay, so L smooth, I mean that the gradient of phi is L ellipsis. Okay? So these informations are needed when you design some optimization algorithm to minimize the phi function. Okay? So let me discuss some proof idea. By duality, okay, what is important, what is difficult is that to differentiate, to find how this EOT cost depends on matrix A, okay, as a function of A. Okay. So by duality, EOT cost can be written, can be expressed using entropic potentials. Okay. In this case, entropic potentials are indexed by A because cost depends on A. Okay. So in the previous case, we think of the entropic potentials as mappings of two marginals. But in this case, entropic potentials are indexed by A, okay? And then we want to understand how these entropic potentials change when you change matrix A, okay? But then I guess you can see some similarity with the previous analysis. Okay, so these entropic potentials satisfy the Schrodinger system that determines these potentials. Okay, so you can apply implicit function theorem to the Schrodinger system to find the Fresher derivatives of the mapping from A to entropic potentials. Okay, so once we can get these derivatives, then you can basically plug in potentials into entropic cost, and then find the derivatives of the entropic cost with respect to matrix A. So that's what we have done in the paper. Actually, in this problem is actually much more standard than the previous case, because we are just working with the matrix, right? So you have a set so we have a space of matrices which is finite dimensional. So you don't have to kind of find some funky space, and then you don't have to embed marginals into some funky space, right? So we can simply work with the space of matrices, okay? And in this, yeah, go ahead. Oh, so actually, I'm not sure whether this lower bound is sharp. Yeah, I think possibly, I mean, depending on the problem, I think you can get a better lower bound for epsilon. Yeah. So we wanted to kind of get some clean lower bound, but actually there's a kind of complicated bound, but I'm just presenting some clean lower bound for epsilon. Yeah. So it's convex in A. Your cost is linear. This cost function C is linear in A, yes. Yeah. Well, the cost should be smoothing A, otherwise smoothing concave. Yes, I think so. Yeah, I think so. Yeah. Oh, this is because this is appearing in the this variational representation of the Gromov-Wasserstein distance. So yeah, so yeah. Okay. So this is something not I chose, but it's basically coming from the variational representation of the entropic GW cost distance. Okay. All right. Okay. Any questions? No? Okay, so once we have this information, then we can basically adopt any kind of smooth optimization tool to compute the entropic Gromov-Wasserstein. For example, for convex regime, we adapted the method of Dascoux-Dumont to get the optimal convergence rate, where k is the number of iterations. So the adaptation is given here. Okay. And also for non-convex regime, we adapted the method of Gadim and Lan to get some guarantees for this method. So in the latter case, the objective is non-convex. So what we can expect is to get the stationary points. Okay, so what we did is basically after some iterations, the size of the gradient is small enough. So this is something we did. Okay, and how small it is, and we quantify how small the gradient is as the number of iterations grows. Okay. Okay. And and also both cases, the computational cost is n squared. Okay? Yep. Oh, okay, I see. So EOT problem. So this is minimizing, optimizing over pi, and possibly you can kind of okay. So I see. So okay, so you can move this minimization outside of this loop, and then you have misinf of A and inf of pi, and then you have this objective, new objective. I see. I see. That's a good point. I'm not entirely sure, but since the original problem is non-convex in pi, so I'm not sure whether this is really, this this one is eventually convex in A and pi. So EOT is convex in pi, yes, yeah. Yeah, but EOT, you can compute EOT by using synchron. So EOT you can compute. Okay. So EOT we can compute. So that's something we are doing. So we can compute EOT, fine. But then the question is like how we have to further optimize, minimize the function phi, which depends on EOT cost through A, the matrix A. Okay. Right. Okay. Okay. And in both cases, the computational cost is n squared when both marginals are supported on endpoints. Okay? So the actual computational cost is n squared times the number of iterations. Okay? But of course, number of iterations depends on the precision parameter you can choose. So n squared times the number of iterations. Okay? But if you fix the precision parameter, then the number of iterations is just a fixed constant. So we are assuming that that is fixed constant. Okay? Any questions? All right, so okay, so previously we just I focused on computation or optimization of entropic GW distance, but you might wonder how we can use that result to compute the GW itself. Okay, so we have so of course GW optimization is non-convex, so it's quite difficult to really globally optimize the GW problem. But we have some implication from our study, so which basically says that all right, so we minimize this. Okay, so when epsilon is small, then this is kind of non-convex, but still we can compute like stationary points for this this objective. Okay, then so we have shown that any cluster point of stationary points for the objective, okay, when epsilon is going to 0, is also a stationary point, stationary for the limiting function. Okay. So this essentially means that as long as epsilon is small, then any stationary points for this objective are roughly approximately stationary for the GW objective. Okay. Okay. So this is nice picture Gabriel created. Anyway, so okay, I think I have 10 more minutes, so let's talk about the last topic. So inference for the GW distance. So okay, so we discussed how to compute EGW or GW, but okay, so so we wanted to understand how to kind of make inference for the GW or EGW. Okay? But this area is currently quite wide open. So even for discrete marginals, deriving asymptotic distribution for GW is quite difficult. It's quite challenging. So I'm presenting one special case where each marginal is discrete. In that case, okay, so you have n and you have n. So these are empirical distributions of the NID data. And what happened is that so limiting distribution is given by a minimax of some Gaussian process. Okay. I won't discuss like what these notations are because they are not really kind of intuitive and not really helpful. But anyway, the point is that limiting distribution is quite complicated. Okay. So and also non-Gaussian limit. So you get what you get is minimax of some Gaussian process, right? So when two marginals coincide, then you can simplify. Well, when up to some isometry, then you can simplify this limiting Gaussian limiting process. And in that case, so we actually propose some way to simulate the limiting distribution, okay, without computing GW many times. Okay, as I said before, computing GW is quite difficult. So in that case, we don't like to kind of use like bootstrap or subsampling, okay, to simulate this, to approximate this distribution, because if you use subsampling, then you have to compute GW many times, which may not be quite easy. Okay, so instead of doing that, we propose a way to kind of simulate, you know, this distribution by directly simulating Gaussian process. Okay, so that's what we did when population GW is T. Okay. Anyways, okay. So proof idea is to establish the derivative of the GW with respect to mu and nu. In this case, mu and nu are both discrete, so we can parameterize mu and nu by the finite dimensional vectors, right? But in this case, GW is not differentiable, as you can imagine. If this is differentiable, then what you get is Gaussian distribution. Okay, so this mapping is actually non-differentiable, but still this mapping is directionally differentiable. Okay, but establishing this was quite challenging. Actually, what we did is first to find the Kato directional derivative. To do so, we first find the upper bound and lower bound, and then to find the upper bound, we kind of did some relaxation, and then show that this relaxation is tight. Okay, and then we needed several techniques for optimization to really kind of show that these two bounds match in the limit. Okay. And also we explore other cases such as semi-discrete case where the input is continuous while the output is discrete, and also EGW distance. So the latter case is much more regular. So EGW is actually kind of easier to analyze. Okay, but still, I think still there's some non-trivial techniques used there to get asymptotic distributions. Any questions? Okay. Okay, so let me wrap up. So for the entropy of transport, I discussed like unified limiting distribution theory that leads to kind of, you know, asymptotic distributions of EOT object under the same umbrella. And key to our analysis is the stability of the entropic potentials with respect to the marginals. Okay. And for the entropic GW, for GW distance, I discussed like formal computational guarantees for the entropic GW. Again, key to our analysis is the stability of the entropic potentials with respect to the metrics appearing in the cost function. Okay. And finally, I discussed like limiting distribution for the entropic GW and entropic GW. Okay. Any questions? If not, then thank you so much. Good. Yeah, sure.
I have a very naive question.
Yep.
The question is why, in which scenario we will be interested in knowing the limiting distribution of the entropy cost. So what would be one useful case from one such theory that we can use?
Well, you can think of EOT as kind of surrogate of OT, so you can apply EOT to do some testing. I think Zaid has a paper on independent testing for using the EOT for synchron divergence. Okay. And then you can use like this limiting distribution to calibrate critical values for the test statistic. Okay.
So I'm doing this on the test.
Well, you can, basically EOT cost or synchron divergence are surrogate of the OT cost, right?
Yeah.
So, I mean, you can basically apply standard applications of OT cost to EOT case as well. And then you can use these limiting distributions to, you know, to do like valid inference for EOT cost or synchron divergence.
Yeah, and there has to be a task I'm interested in inferring the EOT cost. I can imagine, for example, in some goodness of fit test situations.
Yeah, two-sample testing or goodness fit testing or like those like standard testing problems, you can apply EOT or synchron divergence. Yep. Yep. Oh yeah.
Is there a dynamic version of Entropic CW as in learning methodology?
So that's a good question. So I think there is a paper by Zenshin, which explore dynamical formulation of the GW problem. Yeah, there is. Yeah.
I have a quick question on slide
Yeah.
24. So I just, in the complexity you said,
Yeah.
slide 24.
24, yes, 24.
You said you consider the complexity of a fixed
Yeah.
number of iterations.
Iterations, yes.
Why is that relevant? Presumably with the accuracy.
Yeah, of course, yes. Yeah, well, so if you fix accuracy parameter, then number of iterations is fixed, right? Yeah. But then there's this convergence rate. You can basically kind of also compute how. So k 1 over k squared. So so if you wanted to make the error to be less than, let's say, epsilon, or maybe like delta or something, then you need to have roughly 1 over square root of delta iterations, and that parameters will should be added this cost.